Namaste everyone. Welcome back to the physics class. Hope we are doing well. In the previous class, we have studied about the law of conservation of mechanical energy, and we applied it in the case of a freely falling body, and using that law of conservation of energy, we were able to get the equations of motion. What is all about law of conservation of energy? The total mechanical energy of a system must always remain constant. In the case of a freely falling body, the total mechanical energy at different positions of the object must be the same. Using that concept, we were able to get equations of motion. Today in this class, we will apply the law of conservation of energy to a particle moving in a vertical circular path, and we will try to get the velocity at different positions of the object. Right? And you know that whenever a particle moves in a circular path, centripetal force is a must. And here is one more force that is coming into picture. If you take a particle and make it to move in a horizontal circle, of course, weight acts on the particle at different positions, but its direction doesn't change. That in the sense, it doesn't go along with the centripetal force, or it doesn't go against the centripetal force. When the particle moves in a horizontal circle, weight is always vertically down like this. Centripetal force is always along the radius and towards the center. They will always be perpendicular, so there is no difference in the resultant force. Whereas, when the particle moves in a vertical circle, sometimes weight acts along with this centripetal force. Sometimes weight will be in the opposite direction of centripetal force. So there is a tug of war between the two. So now we have to take a particle of mass m along with a string of length L, tie a string of length L to the particle of mass m, rotate it in a circular path like this. So when you rotate it in the circular path, vertical circular path, there is a condition here that you must give a velocity at the bottommost position in such a way that you are not allowed to move it every here and there. Just give a tangential velocity. Suppose you have the bob of a simple pendulum like this, just throw it away like this in the tangential direction. It keeps on moving like this, but as it moves up, its velocity keeps on decreasing. By the time it reaches to the top, its velocity shouldn't become zero. Condition is velocity shouldn't become zero, but tension in the thread should become zero. What do you mean by the time it reaches the top, tension should become zero? The meaning is very simple. By the time it reaches the top, centripetal force is a must. That responsibility of centripetal force must be taken by the weight, the gravitational force, and the tension in the thread should become zero, because tension shouldn't take the responsibility of centripetal force. Weight should take the responsibility of centripetal force. So by the time the body reaches the top, the thread should be having zero tension, and that is what we use the word here. Thread stackens, or the string stackens at the top. We use this word, stackens. That means tension should become zero, right? I will explain it again. So now consider a particle of mass m taken in a thread, tied to a thread, and made to move in a circular path of radius L, right? Suppose L be the length of the thread, and let it be made to move. And we are not allowed to pull it again and again. Just give the tangential velocity only at the bottom position. Let it go by itself to the top. That is the condition here. Okay, so let me give a velocity here. Let V0 be the velocity at the position A. I call it as V0, tangential velocity. V0 in the sense it is the initial velocity. By the time it reaches here, let the velocity be VB at the position B. And by the time it reaches to the top, let the velocity be Vc, again tangential, at the position C. Mass of the bob doesn't change anywhere. It remains the same everywhere. So this is the mass of the bob. So I think you have understood what we are going to do today, right? You are considering a particle which is given a tangential velocity at the bottommost position, which is V0, and you are allowing it to move in the vertical circle. But my condition is the velocity should be at least such that by the time it reaches the top, the string stackens. That means tension in the string must become zero. I'm not talking about velocity becoming zero. If velocity becomes zero at the topmost position, what is the situation then? If the velocity becomes zero, centripetal force itself is zero. Body will not continue in the circular path. By the time it reaches the top, if velocity becomes zero, simply the weight will put it down. The journey of the particle will be like this, right? It goes to the top, velocity becomes zero, and simply comes down. That is not the situation now. Some velocity should be retained out of V0. Vc should be retained, so that by the time it is at the top, that velocity will create the need of some centripetal force, mv squared by r. That should be provided by the weight, not by the tension in the thread. So tension should become free. It will give all the responsibility to the weight. Weight will take the responsibility of centripetal force. Tension becomes free. That's what the word string stackens at the top. It becomes free from tension. So under that condition, what is the velocity needed at the bottom? How much velocity should be given at the bottom? That is our condition now. In order to get that velocity here, maybe the velocity Vb, also the velocity Vc, how much is that? If you want to get it, apply the law of conservation of energy. That is, total mechanical energy at all the positions must remain the same. There should not be any change in the mechanical energy. Okay, and so now let us try to write the different positions and the forces at different positions. You know that centripetal force is always directed towards the center along the radius, and tension in the thread, usually when you rotate it in a horizontal circle, tension in the thread provides the centripetal force, and the tension is always towards the center like this. So if I go on writing the tension at A, I'll write tension at B. It should be always like this. Tension at C. So it is like this. Now there is one more force which is coming into picture here. Weight. Weight is always downwards, you know that. Earth attracts all the objects towards its center, so weight always acts downwards. What is the weight of the body here? Let me write the position A somewhere else. So I will write it here. Position A. Weight is always acting what? Mg downwards. What about mg here? Here also it is downwards, mg. So we have mentioned all the forces. Of course at B it is not needed. At B we will get the equation once you get the condition here at C. We can use that and find out what is the velocity at B. So weight is downwards. Tension is always towards the along the radius towards the center, because tension usually takes the responsibility of or takes the part of centripetal force. But centripetal force is a must. Whether you take it in the form of tension, whether you take it in the form of tension in the thread, I mean, whether you take it in the form of gravitational force, whether you take it in the form of electrostatic force, in whatever the form you take, centripetal force is a must. Now, if you want to write the formula for centripetal force and at different positions, okay, I'll write the positions. And before that, one more thing. Let me try to write the positions of the objects in terms of heights. See, by the time the object reaches here, what is the height? What is the height of the object reached? You know that gravitational force is conservative force. So when you move from one position to another position, how much energy is changed? That doesn't depend on the path. And it is the direct position or direct distance from the initial to final position. It doesn't depend on the total path. Initial and final positions are all only the important things. So shall I write the height here as okay, this height is L, right? By the time the body reaches from A to B, h is equal to L. By the time the body reaches from A to C, height is 2L. Am I right? This is 2L. Let me try to use the space because I want to write all the equations. So when the particle reaches here, the height it has attained is L. By the time it reaches here, height is 2L. Correct? Okay. Now we will write different forces at different positions, right? So I will write position A and position B, position C, right? At A and at C. At A and at C. We will write the conservation of energy and total centripetal force, everything at different positions. At A. Now at A, there is only one energy. I'll take this as reference. This is the reference height. From here, the body starts moving up and up. By the time it reaches here, height is h. By the time it reaches here, height is h is L. By the time it reaches here, height is 2L. But here, height is 0. So at A, I am giving only the tangential velocity, and the bob of the simple pendulum is just given a tangential velocity. So velocity is V0 here. What about the kinetic energy? Half mv square. What about the potential energy? 0. So at A, body has got total only kinetic energy, half mv0 square only. Only kinetic energy. Why? because there is no potential energy. Height is 0. From the reference level itself is the bottommost position of the pendulum. And you shouldn't start it from Earth, because it keeps on moving its journey in only circular path. It never comes to the that surface of the Earth. It keeps on rotating in this position only. So this is the reference position. No potential energy, only kinetic energy. Okay. Shall I put a fence here? Yeah. And I have to write this here. Yes. Now, what about the net force acting on the body? How will be the centripetal force here at A? At A, of course, that equation doesn't help you. This equation helps you. Total energy at A is half mv naught square. And similarly, okay, we will complete this. What is the total energy at C? Okay, I'll put a fence, one more fence, so that I can divide the board as I want. Yes. Is it okay? Right. What is the total energy at C? Total energy at C is both kinetic as well as potential. Kinetic is half m Vc square. One more fence here. Is it okay? Is it a straight line? Right? Vertical line? It's okay, almost. Half m Vc square plus mg h. H is 2L. Total energy at C. By the time it reaches C, it has retained certain velocity Vc. Its velocity has not become 0 by the time it reaches here. There is a velocity Vc, so there is kinetic energy half m Vc square, plus there is a potential energy. It has gone to a height of 2L, mg into 2L. Equation, okay, I'll write it as 2, no problem. Now, what about the forces? If I write the force here, okay, force, net force here. See, always tension in the thread must be the centripetal force. What about here at A? Centripetal force is mv naught square by r. R is radius, that is L. Velocity is v naught. mv squared by r must be equal to the tension. That should be acting like a tension. But there is one more force which is acting here, that is weight of the body. Right? Weight is opposite to the tension here, tension in the thread. So that weight will also add to the tension. So tension is equal to mg plus mv naught square by r. Do you get that? So tension is equal to mg plus mv naught square by r. Suppose you take a particle in a horizontal circular path like this. You know that only the tension will take place or take the role of centripetal force. Tension itself will act like a centripetal force. Because weight is vertically downwards and it is at 90 degrees, component of weight in this direction is 0 when it is moving in the horizontal circle. Horizontal circle alli particle ಹೋಗ್ತಾ ಇರುವಾಗ particle ಗೆ centripetal force ಇಲ್ಲಿರುತ್ತೆ, ಅದೇ ಟೆನ್ಷನ್ ಆಗುತ್ತೆ. weight ಇಲ್ಲಿರುತ್ತೆ vertically downwards, ಅವಾಗ 90 degree ಆಯಿತು. What is the component of the weight in this direction? 0. So no weight will disturb for centripetal force. But ಇಲ್ಲಿ ಆಗುವಾಗ the tension is acting here, weight is here. So tension is created also by weight. So mg plus mv squared by r. Okay. What about here? And our aim is by the time the object reaches to C. C ಗೆ ಬಂದಿರುವಾಗ ನಮ್ಮ aim ಏನು ಅಂತ ಹೇಳಿದ್ರೆ the tension in the thread should become 0. But along with the tension we will write the formula. Tension ಅನ್ನು ತಗೊಂಡೆ ಫಾರ್ಮುಲಾ ಬರೆಯೋಣ. Tension ಒಂದು mv squared by r ಅನ್ನ tension ತಗೋಬೇಕು, right? Tension at C must be created by mvc squared by L, right? ಇಲ್ಲಿ radius ಆಗಬೇಕು, right? This is not 2L, radius ಆಗಬೇಕು ಇದು. Here also it is radius. Hope you can follow this. ಅದೇ ನೀವು potential energy at C ಬರುವಾಗ mg 2L ಆಗಿ ಬರಿತೀವಿ ಅಂತಾರೆ, height 2L ಆಗಿದ್ದು. Here it is mv squared by r, radius. So the centripetal force at the top is mv squared by r. ಅದನ್ನ ಟೆನ್ಷನ್ ಕೊಡಬೇಕು. But tension ಜೊತೆಗೆ ಇನ್ನೊಂದು ಫೋರ್ಸ್ ಇಲ್ಲ ಅಲ್ಲಿ, mg, it is in the same direction. So is it tension plus mg is equal to mvc square by r or L? Tension plus mg, ಇಲ್ಲಿ centripetal force ಈ ಡೈರೆಕ್ಷನ್ ಬರಬೇಕು. ಸಿಂಪಲ್ ಆಗಿ ಹೇಳೋದಾದ್ರೆ, if I can give the idea in the simplest form, it is like this. Centripetal force ನಮಗೆ ಯಾವ್ದಾದ್ರು ಒಂದು ಫಾರ್ಮ್ ಅಲ್ಲಿ ಬರಬೇಕು. ಇಲ್ಲಿ centripetal force is given by mv square by r. But mg ಅದಕ್ಕೆ opposite ಇದೆ. So tension minus mg is centripetal force. Am I right? ಈ ಡೈರೆಕ್ಷನಲ್ಲಿ ಸೆಂಟ್ರಿಪಿಟಲ್ ಫೋರ್ಸ್ ಬರಬೇಕು, ಟೆನ್ಷನ್ ಮೈನಸ್ ಎಮ್ ಜಿ ಸೆಂಟ್ರಿಪಿಟಲ್ ಫೋರ್ಸ್. ಇಲ್ಲಿ ಸೆಂಟ್ರಿಪಿಟಲ್ ಫೋರ್ಸ್ ಈ ಡೈರೆಕ್ಷನ್ ಬರಬೇಕು, ಅದು ಟೆನ್ಷನ್ ಪ್ಲಸ್ ಎಮ್ ಜಿ ಆಗಿದೆ. ಸೊ ಟಿ ಪ್ಲಸ್ ಎಮ್ ಜಿ ಈಸ್ ದ ಸೆಂಟ್ರಿಪಿಟಲ್ ಫೋರ್ಸ್, ಎಮ್ ವಿ ಸ್ಕ್ವೇರ್ ಬೈ ಆರ್. So this is at C, this is at A, that is the 0th position, in the sense at the 0th time. Okay, now if the tension is 0, if the string stackens at the top, tension 0 ಆಗಬೇಕು ನಮಗೆ, thread free ಆಗಿರಬೇಕು top most position ಗೆ ಬರುವಾಗ. If the thread has to become free at the top most position, who will give the centripetal force then? Weight ಇದೆಯಲ್ಲ, weight will take the responsibility of centripetal force. mg must be taken by mvc square by r, mvc squared by l. So this is equation 3 ಅಂತ ತಗೊಳ್ತೀನಿ ನಾನು. Weight is balanced by the centripetal force, or centripetal force is given by the weight itself. ಈಗ ಥ್ರೆಡ್ ಫ್ರೀ ಆಯಿತು, ಥ್ರೆಡ್ಗೆ ಏನು ಕೆಲಸ ಇಲ್ಲ ಇಲ್ಲಿ, ಅಂಥ ವೆಲಾಸಿಟಿ ಉಳ್ಕೊಳ್ಳೋ ಹಾಗೆ ಇಲ್ಲಿ ವೆಲಾಸಿಟಿ ಕೊಡ್ಬೇಕು ನಾವು, ವಿ ನಾಟ್. Okay, now I want to club the things now. My question is, what should be this velocity so that by the time it reaches here, the tension in the thread becomes 0. Okay, so adana mix up ಮಾಡ್ಕೊಂಡು ಹೋದ್ರೆ ಆಯಿತು. You mix it up, I'll stop it here for both the things. Okay, now I'll take the law of conservation of energy, the help of law of conservation of energy here. Law of conservation of energy help ತಗೊಳ್ಳೋಣ. You know that total mechanical energy of this whole system, here, 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 ಎಲ್ಲ ಕಡೆಗಳಲ್ಲಿಯೂ ಟೋಟಲ್ ಮೆಕ್ಯಾನಿಕಲ್ ಎನರ್ಜಿ ಸೇಮ್ ಇರಬೇಕು. ಅಂದರೆ ದ ಟೋಟಲ್ ಮೆಕ್ಯಾನಿಕಲ್ ಎನರ್ಜಿ ಅಟ್ ಓ at the 0th position, mechanical energy at this position C must be same. ಅಂದರೆ E naught must be equal to EC. Am I right? What is E naught? Half mv naught square. Only kinetic energy must be equal to the total energy at C, half m vc square plus 2 mgl. Am I right? 2 mgl. ಇದೆರಡು ಸೇಮ್ ಇರಬೇಕು ಎನರ್ಜಿ. Okay, but we will take the help of this one also. At the topmost position there should not be any tension in the thread, means weight will give you the centripetal force. mg must be given by mv square by l. Okay, ಹಾಗಿದ್ರೆ ಅದನ್ನು ಹೇಗೆ ನಾವು ಕ್ಲಬ್ ಮಾಡ್ತೀವಿ ಇವಾಗ? We will use this one. ಇದನ್ನು I'll write it here. Okay, or I can write it here itself. ಇಲ್ಲೇ ಬರ್ಬಿಡೋಣ. This is easy. ಇದನ್ನು ಸ್ವಲ್ಪ ಶಾರ್ಟ್ ಮಾಡ್ಕೊಳ್ಳೋಣ. m is squared by l, that implies mgl is equal to mvc squared. I'll take this as equation 4. ಸುಮ್ಮನೆ ನಂಬರ್ ಆಗ್ತಾ ಹೋಗೋಣ. mgl is equal to mvc squared. So substitute this here. ಇದನ್ನು ಇಲ್ಲಿ ಹಾಕೊಳ್ಳಿ. So what you will get? Half mv naught square. We will use this equation now. Is equal to half mvc square. Now can I use mvc square is nothing but mgl. So half mgl, right? mvc square is replaced as mgl plus 2 mgl as it is. Let us try to express the velocity at O so that the tension becomes 0 here. We have to express V naught in terms of L. Now you can take m outside common and you can cancel. M and L cancel ಮಾಡಿಬಿಡ್ಬೋದು. So what will remain now? V naught square by 2 is equal to GL by 2 plus 2GL. That implies V naught square by 2 is equal to, take the common denominator, 2 here, 2 ones are 1 GLs are GL plus here 1 2s are, so 4GL. So you will get V naught square by 2, V naught square by 2 is equal to this one 5GL by 2, right? 2 gets cancelled. What is V naught? V naught is equal to square root of 5GL. This is the equation what I was expecting. V naught, I can't write it here at the bottom. V naught is equal to root of 5GL. So this is the minimum velocity depending on the length of the thread. This is the minimum velocity that you have to give at the bottommost position, so that by the time object reaches to the top, the tension in the thread becomes 0 and it continues the journey in the by taking weight itself as the centripetal force at that position and continues to move in the circular path. So minimum velocity is root of 5GL. Now what is the velocity by the time it reaches B? At B. At B you write the total kinetic energy formula. Total mechanical energy formula at B. At B, total mechanical energy is given by EB is equal to, so there will be both kinetic as well as potential. Kinetic is half mVb square plus potential is mgh, mgl only, because height by the time it reaches here is L. Height is L. So mgl plus half mVb square. Now according to law of conservation of energy, don't write it like this, right? Law of conservation of energy, energy at O and energy at B must be equal. They must be equal, because total mechanical energy, whether it is here or here or here or here, everywhere it should be same. That means half mVb square, okay, plus mgl must be equal to the total energy at the bottommost position, that is half mv naught square. We have E naught. E naught is half mv naught square. Half mv naught square. Okay. M can be taken outside and it can be cancelled, or we can substitute the velocity v naught. V naught is root of phi gl, right? Then we will get Vb. Okay. So m can be cancelled. M will be cancelled. Vb square by 2 plus gl must be equal to half v naught square. What is v naught square? Phi gl. Root of phi gl whole square. That is from this equation, previous obtained equation. So what you will get then finally, Vb square by 2 plus gl must be equal to this is the square phi gl, phi by 2 gl. That implies, I'll write it from this end, Vb square by 2 must be equal to phi by 2 gl minus gl, that is equal to 2 common phi gl minus 2 gl, that is equal to 3 gl by 2. Vb square by 2 is equal to 3 gl by 2. 2 gets cancelled. What is Vb? That implies Vb is equal to square root of 3 gl. So by the time it reaches the position B, its velocity will become root of 3 gl. So we have got the velocities at different positions of the object. Now if you are asked to find out what is the ratio of kinetic energy of the body at O and B, ratio of kinetic energy. Ratio of kinetic energy at O and B. Kinetic energy at O by kinetic energy at B must be equal to, or kinetic energy at C if you want to write. Anyway, kinetic energy at O and kinetic energy at B, right? That is half m V naught square divided by half m Vb square. That is equal to, half m gets cancelled, that is V naught square by Vb square. What is V naught square? It is 5 gl divided by 3 gl, because half m gets cancelled. Only Vb square and V naught square will remain. V naught squared is 5 gl, Vb squared is 3 gl. Is it 5 by 3, right? So the ratio of kinetic energies of the body at O and B will be 5 by 3. So that is another outcome of this equation. So you will be asked to derive this one. Very rarely asked for the final exam, but for entrance exam this is very important. So just know the formulas, and the way in which we arrive at it, that is also important. Not the derivation, but the process of derivation. Why did you take the tension here and weight here? What is the net tension here? What is the net tension here? What is the centripetal force at different positions? And what is the total energy at different positions? All these ideas of information of different energies and tensions are very much required for working out problems, right? Hope you have understood this. If at all you have any doubt, please message me, we will solve it, and study this derivation properly. Thanks for watching my class. We will meet in the next class with different types of forces and energies. Thank you.